So, now the next set of discussion involves the extension of these ideas of variational symmetry to functionals having integrands with several dependent variables. So, what I said is that the notion of variational invariance, can be extended to functionals of several dependent variables, right. Several dependent variables given, let us say those variables are q1, q2, q1, right. Okay. So, we consider the functional j of q bar, which is also equal to from t0 to t1 of L of t comma q bar dot of dt. We consider this general functional. Let me represent this equation by 5, right. And also now we are going to consider transformations of this form. Consider transformations of the form t is equal to theta of t comma q bar comma epsilon and qk is equal to psi k of t comma q bar comma epsilon. Okay. Okay. So, we consider the transformation of this form. Let me call this by 6. Okay. So, again we need to satisfy certain consistency criteria, namely that the transformation for the parameter value epsilon equal to 0 are nothing but the identity transformation. So, we plus we also assume the condition that theta of t comma q bar comma 0 is equal to t and psi of t bar comma q bar comma 0 is qk, right. Okay. So, this is the value, this is essentially I am saying that at epsilon is equal to 0 I am getting back the identity transformation. Okay. So, at epsilon equal to 0 I am getting the identity transformation. Fine. So, then I need to talk about the concept of variationally invariant functionals. Okay. Similar to the case of one dependent variable, I can extend my notion as follows. So, the integrand L of t comma q bar dot is variationally invariant under the transformation given by 6, is variationally invariant under the transformation 6. Under the transformation 6, if for all epsilon such that epsilon is small in any subinterval, well, let me complete this statement. This is nothing but the extension of the result for the case of one dependent variable. So, in the subinterval alpha beta, which is a subset of t0 t1, we get that the integral from alpha to beta L of t comma q bar dot dt. This is also equal to integral from a epsilon to b epsilon of L of t comma q epsilon t comma q bar, well, these are all q bars. So, q bar epsilon of t, right, of dt. Okay, so the integrand is variationally invariant if I can find if I can see that my integrand retains the same form when transforming from one coordinate to the other, right? And so where my a epsilon, again similar to our one variable case, is theta of alpha comma q bar alpha comma epsilon, and my beta of epsilon is theta of beta comma q bar beta comma epsilon. Okay, where I denote my dot to be differentiation with respect to t, right? I have the variable t here, so this dot represents the derivative with respect to t, and this dot well, let me erase this. So this dot represents the derivative with respect to the variable capital T, right? Okay. So let us look at an example for the multiply dependent variable case, see how the ideas of transformation works, right? So the example I have is as follows. So suppose let my n be equal to 2, t0 equal to 0 and t1 is equal to 1, and let us say that L of t comma q bar dot is equal to 1 by 2m of q1 square plus q2 square plus. So I am just introducing, so this, in this case my Lagrangian is as follows. Students who are looking at this Lagrangian will immediately recognize that this is the same example that we introduced in example 10 of our previous lecture, that is the central force problem. And I want to highlight similar to the central force problem, right, because we have a plus here. Now these sort of a Lagrangian frequently appears where we have to describe the planetary motion, also known as the Kepler's law, right. So my m and k are constants. So my Lagrangian L here is a Lagrangian which describes my planetary motion via the Kepler's law. Okay, via the Kepler's law. Okay, right, via the Kepler's law. Okay. So let us consider a transformation. To see what sort of transformation this Lagrangian is variationally invariant. So let us consider this transformation. Consider the transformation. The simplest one is the translational transformation. Consider the transformation of the form t is equal to t plus epsilon and q case is equal to q case, right. Now notice that this in this Lagrangian, this is independent, this Lagrangian is independent of the independent variable t. So we have mentioned for integrands of one variable that for integrands which are independent of the independent variable will be invariant under this translational transformation. So what I am saying is that it is easy to show that this transformation is the variational symmetry. Variational symmetry for L. Students should check that by plugging in the respective variables, right. Okay, so where here my k is 1 and 2. So we have three relations here. So let us look at a more non-trivial case. So let us consider another transformation of the form capital T is equal to T and Q1 is equal to Q1 cos epsilon plus Q2 is equal to q2 sine epsilon, and capital Q2 is equal to minus q1 sine epsilon plus q2 sine, well, q2 cos epsilon. And I see, let me call this transformation by 7, because so far we have introduced relations up to 6, right. So that is what we have done here, is it? Yes, we have introduced relations up to 6. So 6 was my transformation, the general form. Okay, so we have called this rotational transform. So this is my rotational transformation. Okay. So let us look at what happens under this transformation. What is the form of my Lagrangian? So which means for this transformation 7, I see that dt is small dt, because the way we have set up the variable, and my capital Q1 dot, the Q1 dot is derivative, well, I need to be careful here. Well, the way we have, let us just quickly go back. Well, I think we are fine. We are fine here. So Q1 dot, well, notice the following, where Q1 is Q1 times cos epsilon and sin epsilon. So the only dependence of the variable t, which is small t, is via Q1 and Q2. So when we take the derivative, we are differentiating the variables small q1, small q2, because epsilon, the parameter epsilon is fixed, right. So my variable q1 dot is q1 dot cos epsilon plus q2 dot sin epsilon, right. And my variable q2 dot is equal to minus q1 dot sin epsilon plus q2 dot cos epsilon, right. And so here it is quite clear that my dot is the derivative with respect to the original independent variable t. Okay. So then let us calculate L of t comma q epsilon comma q epsilon dot. Without going into detail what is this dot, it will be clear very soon. Okay. So then my Lagrangian in this new coordinate, let me put a bar because we are talking about multiply dependent coordinates. So it is half m q1 dot square plus q2 dot square plus k by square root of q1 square plus q2 square, right. We plug in the values of q1 and q2 and q1 dot and q2 dot, and we see that this is also equal to half m. So I am just plugging in all the values that we have so far derived. This is also equal to q1 dot cos epsilon plus q2 dot sin epsilon square plus minus q1 sin epsilon plus q2 cos epsilon whole square, right. This is also we have just plugged in these values plus k by, well, k by square root of q1 square plus q2 square. So q1 is q1 cos epsilon plus q2 sin epsilon whole square plus the second quantity is, so q1 minus q2, so minus capital Q2. So this is my capital Q1, and capital Q2 is minus q1 sin epsilon plus q2 cos epsilon whole square, and this is my capital Q2. Note that after simplification, let me write down the form of this function. We see that I am going to get, after all the simplification, the steps here are omitted. We are going to recover back our original integral, our original Lagrangian. So k by q1 square plus q2 square, and that is my L of t comma q bar comma q bar dot. Okay. So what have we found? That the transformation 7, which is the rotational transformation, is the variational symmetry to this problem with the Lagrangian given as follows. Okay. So which means Hence, for any subinterval, remember our original interval was from 0 to 1. For any subinterval of the original interval, it turns out that L of t comma q bar dot dt from alpha to beta, this is also equal to L of a epsilon to beta epsilon, L of t comma q epsilon dot dt, right? Okay. So what have we got? That we have shown this, or the result is that our relation 7 is a variational symmetry. Okay, so that is what we have seen. Okay, we are almost at a point where we are ready to describe Noether's theorem, but there is one more concept that I want to introduce at this point. So that is the concept of infinitesimal generators. Right? Infinitesimal generators. So consider the Taylor series expansion of our transformation functions theta and psi. So consider the Taylor series expansion, of the transformation, x is equal to capital X of x comma y comma epsilon, and y is equal to psi of x comma y comma epsilon, and my epsilon is small. Okay. We see that we are going to do the Taylor series expansion around epsilon equal to 0. So I can say that using Taylor series, x is theta of x y 0 plus epsilon times del theta del epsilon set at epsilon equal to 0 plus higher order terms plus order epsilon square, right? Okay. Similarly, so what we are trying to do is we are trying to represent our transformations up to linear order. We are ignoring higher order. When I talk about higher order, I am talking about higher order with respect to the parameter epsilon. So I am trying to ignore the effects of the higher order terms with respect to epsilon, because epsilon is close to 0, it's small. Okay. So similarly, we can write the other expression. So y is equal to the function psi at x comma y comma 0 plus epsilon del psi del epsilon. Well, we are differentiating with respect to the unknown parameter epsilon set at epsilon equal to 0 plus higher order terms, right? We also denote these functions xi to be our derivatives del theta del epsilon at epsilon equal to 0, and my eta to be del psi del epsilon at epsilon equal to 0. From here I get the so-called, so these are my so-called infinitesimal generators. Right? So from here we can extend the concept of infinitesimal generator to functions of several dependent variables. So similarly for multiple dependent variables, functionals, I see that my infinitesimal generators are xi of t comma q bar. Now in terms of the variables q bar, this is going to be del theta del epsilon at epsilon equal to 0, and eta now is a vector. So, for each variable component, for each component corresponding to the variable q case, I have eta k of t comma q bar, which is del psi k del epsilon, right, del psi k del epsilon evaluated at epsilon equal to 0. So, these are my infinitesimal generators in the general case with multiply dependent variables. So, let us now state the so called Noether's theorem. So, in the simplest possible form. So, Noether's theorem I denote it by theorem 20 in the way we are numbering our theorems. So, Noether's theorem, and I am going to denote it by the theorem NT in future reference. So, Noether's theorem says, suppose I am given a function f of x comma y prime is variationally invariant on the interval x naught to x1 under the transformation 3. Again, we are going back to our case of one dependent variable under the transformation 3, where we had described the transformation for one dependent variable with xi comma eta as infinitesimal generators, xi comma eta as my infinitesimal generators. Then what have I got? Then the Noether's theorem tells us the conservation laws. So, what it says is, suppose you give me the infinitesimal generator, Noether gives you the conservation law, right. So, eta del f del y prime plus xi f minus del f del y prime is equal to a constant along any extremal, Okay. So, that is in the simplest form the Noether's theorem. Now, students can immediately recognize that this expression is not new. In the past, we have denoted this first quantity by p and the second quantity here by minus h, and this expression arose in several places, especially when we were discussing broken extremal. So, this expression is not new, okay. And notice that eta and xi are nothing but variation in x or delta x delta y, right. Okay. So, what I am saying is, if my p is, if I introduce the variable p to be del f del y prime and my h to be y prime del f del y prime minus f, then what I see is that the Noether's theorem states that eta p minus xi h is equal to a constant. It is a constant, right. So, this is a constant, fine. Okay. So, let us look at some examples of the application of Noether's theorem. So, the example I have in mind is, I denoted by example 5. So, consider this j. So, j of y given by integral from x0 to x1 x y prime square dx, right. And I am going to consider the transformation x is equal to x plus epsilon 2x log natural log of x, well 2x natural log of x, yes, and capital Y is equal to 1 plus epsilon small y, right. So, which means my infinitesimal generators, my psi is the derivative of theta with epsilon and put epsilon equal to 0, and that gives me 2x log x, and my eta is derivative of psi with respect to epsilon, set epsilon equal to 0, which is also equal to y. Okay, fine. So, we have our infinitesimal generators, and further my p, which is del f del y prime, is also equal to 2x y prime, and my h comes out to be, well, my h is what is my h here? This comes out to be x y prime square. We can just directly, so this is nothing but y prime f of y prime minus, we need to reconsider, minus f. Okay. So, we get back the same expression, h is x y prime square. Okay. So, then so it implies that the Noether's theorem says that the extremals lie on p zeta minus, well, I need to first, so well, there is one thing you need, the students need to verify, we need to verify that that this is a variational symmetry. This is a variational symmetry. So, this transformation leads to a functional in the new variables which is variationally invariant. So, that needs to be verified first, because before we can apply Noether's theorem. So, the Noether's theorem says that this is also equal to p psi, no, so p eta minus h xi, this is equal to a constant, right. So, this is also equal to a constant, fine. So, what have we got here? We have got the following, we plug all these values, and I am going to get the following relation, that x y prime y minus x log x x y prime square, this is also equal to a constant, right. And from here what do I get? I can see that if I differentiate, so the conclusion from here that we get is that the extremals, we can simplify this relation via the following. So, the conclusion that we are going to get, that the extremals lie on the curve given by x y prime whole prime, which is also equal to 0. The extremal lie on this curve. And how did we get that? Let us differentiate. So, let me call this expression as, let me call this expression by phi. So, let us differentiate phi with respect to x and see that this gives us the following, x y prime whole prime times y minus x y prime log x plus x y prime minus x y prime whole prime times log x, right. So, we can see that x y prime whole prime is a common factor in both, and then phi x is equal to 0 only if this, only if this quantity is 0. So, the conclusion is that the extremal lie on this curve, right. So, that comes right from the Noether's result. Okay. So, let us now extend our Noether's theorem for functions of multiple variables, and let us look at an example for that case. So, the version, let me call this Theorem 20a, because this is the extension of the Noether's theorem. It tells us that for multiply dependent variables, for multiple dependent variables q bar, suppose what I have is L of t comma q bar dot is variationally invariant. This is variationally invariant. It is variationally invariant on the interval t0 to t1, right, under the transformation t is equal to theta of t comma q bar comma epsilon, and qk is equal to psi k of t comma q bar comma epsilon. So this is my transformation here, where my q bar is q1, q2, qn, and my xi comma eta k, the set of functions, are my infinitesimal generators. Infinitesimal generators. Okay. So then the result says that summation pk eta k minus h xi, well, is that the way we described it for one variable case? Yes. So summation pk eta k from 1 to n minus h xi, summation this minus h xi is equal to a constant, right? So this is also equal to a constant. Fine. Okay, so that is my Noether's theorem. Along any extremal, along any extremal of jq, which is integral from t0 to t1 L of this function, right? So let me quickly write down this result, where pk is the derivative del L del qk dot, and my h is summation pk qk dot minus L. Fine. So let us look at an example. In this situation. So the example that I have is, this will be the final example of our discussion. So consider our Lagrangian of the form L of t q bar comma q bar dot. So I am taking a vector here. This is a 2D problem. So this is m by 2 q1 dot square plus q2 dot square plus k by square root of q1 square plus q2 square, right? And let us, so then we can see that if I take this transformation t is equal to t plus epsilon and qk is equal to qk, this is certainly a variational symmetry, because in this case my xi, which is the derivative of t with respect to epsilon, set epsilon equal to 0. So derivative of t with respect to epsilon, set epsilon equal to 0 is 1, and my eta is del qk. So my eta k is del epsilon, this is equal to 0. So my Noether's theorem says that I am going to get the conservation law h is equal to a constant, right? Now if I take so if I consider this transformation, consider the transformation t is equal to t, that is a rotational transformation, q1 is equal to q1 cos epsilon plus q2 sin epsilon, and q2 is equal to minus q1 sin epsilon plus q2 cos epsilon. And from here I can see that via the Noether's theorem that my infinitesimal generators xi is equal to 0, my eta 1 is the derivative of q1 with respect to epsilon, set epsilon equal to 0 will give me q2, and my eta 2 is going to give me, after taking the derivative, will give me negative q1. And from here my Noether's theorem tells me that the conservation law is q1 q2 dot plus, well, minus q2 q1 dot is equal to a constant. This is along the extremals q bar, Fine. Okay. So let's look at an extension of this problem, and that so the extension of this problem is another one. So let my q bar of t be q1. So I am talking about a problem in 3D, right? Denote the particle position. So let us look at a problem in Newtonian mechanics. and then my kinetic energy for this system T of q bar will be half m q1 dot square plus q2 dot square plus q3 dot square. Fine. And my potential energy will be V of q bar, which is, well, V of T comma q bar, which is also equal to the sum function. Let me keep it as it is. Then my functional is given by integral from T0 to T1 L. So, L dt, where my Lagrangian L is T minus V, right. So, now students can check that if we were to look at these sort of transformations. So, if I take this transformation, T is equal to T plus epsilon, that is a translational transformation, Qk is equal to Qk. I see that my infinitesimal generators are xi equal to 1, eta k equal to 0, and my Noether's theorem tells me that I get H, which is, it turns out to be T plus V is equal to a constant. Essentially, for this transformation, well, for this transformation, I am satisfying the conservation of energy, right. I am satisfying the conservation of energy. On the other hand, if I take T equal to T and Qk to be equal, well, Q1 to be Q1 plus epsilon and Qk to be small qk, I see that my psi equal to 0, eta 1 is 1 and eta 2 is equal to eta 3 equal to 0. I see that my Noether's theorem gives me mq1 dot equal to a constant, or this is nothing but the conservation of linear momentum. And finally, the last observation is the following: if I take T equal to if I take the rotational transformation, Q1 to be Q1 cos epsilon plus Q2 sin epsilon and Q2 to be minus Q1 cos, well, minus Q1 sin epsilon plus Q2 cos epsilon, and finally my capital Q3 is Q3. I see that my infinitesimal generators are psi equal to 0 and eta 1 equal to Q2 and eta 2 equal to Q1 and eta 3 equal to 0. From here I get the conservation laws P1 Q2 minus P2 Q1 equal to a constant, and we can see that this is the z component of the angular momentum, and hence we are satisfying or we are conserving angular momentum in this transformation. So, thank you very much for listening, and in the next lecture I am going to primarily talk about how to find these variational symmetries. It turns out that once we are able to find these variational symmetries, the Noether's theorem can easily take care of the conservation laws. So, thank you very much.